So, very good morning to one and all. So, welcome to VLSI's class, VLSI design class. So, in the last class, we discussed about the BiCMOS drivers, right? In the last class, we discussed about the BiCMOS drivers. Now, let's go to start the propagation delays. Okay, let's consider that propagation delays. Okay, so just observe the screen. So this is the propagation delay. Okay, so in the propagation delay, that means there are two. This particularly in case of VLSI, we are using the fast transistors and also we are using different layers. Okay, so whenever the signal is passes through this fast transistor or the signal is passes through polysilicon, okay, or sometimes the signal maybe there is a possibility to transmit the signal transmit the signal using the diffusion layers also. Okay, so but what happened if you consider the signal to pass from one point to another by using a fast transistor? Similarly, if you consider the polysilicon layer to propagate the signal from one point to another, and what happened if you consider diffusion layers to transmit the signal, that will propagate the signal from one point to another. We'll discuss now in this section. Okay, so let us consider. First, we can go for the cascaded fast transistors. Okay, let us consider a cascaded fast transistors, and as we know that in the MOS technology, we are using fast transistors as switches. Okay, fast transistors as switches in logic circuits. Okay, it may be either a series connection or it may be a parallel connection. Okay, so there is the main the type of freedom we are having in the MOS technology. You can use the fast transistors as either in series or the parallel switches in the logic circuits. So therefore, the logic signal in that case, what happens? There is a chance of the signal will be must transfer from one point to another using a fast transistors either connected in series. Okay, so whenever this logic signals passes through the fast transistor in series, so what happened in the what happened to that circuit, that signal? We'll discuss now. Let us consider a chain of four transistors, four fast transistors connected in series. Okay, the chain of four transistors which are connected in series like this. Okay, now just observe in this case. These are the fast transistors which are connected in series. Okay, that means drain of the one transistor and this is the source of the transistor. The source of this transistor be connected to the drain of the transistor. Again, drain, so be connected in the same way like this. So this is the fast transistors, and the gates will be joined together. And always can apply a VDD level in order to activate these fast transistors. Okay, in order to activate these fast transistors, always the gate of all the transistors be driven by the VDD signal. This logic high you can consider. And in this condition, so what happens? We can do this is the input terminal and this is the output terminal. When the input voltage is applied, assume that the input signal is changed from 0 to high. In 0 to high at t is equal to 0. That means at t is equal to 0, there is the abrupt change. Okay, there is a sudden change. So therefore, the signal changes from 0 to 1. That is VDD. So when this type of signal is applied to the fast transistor, and that signal passes from one fast transistor to another like this, and reaches the output at this point. So what happens? There is some delay, and the signal there is a sudden rise here the input side, but the output will take some time to reach the value of VDD. But the voltage, the output voltage will not reach the value of VDD because the threshold voltage of these fast transistors. Okay, so therefore the output voltage is equal to VDD minus VTP. Already we have seen in the fast transistor structures. Okay, VDD minus VTP, where VTP is the threshold voltage of the fast transistors, and this is that means you are having the signal be like this. Okay, there is exponentially rises like this. Instead of getting a sudden rise here, so you are having exponentially rising. Okay, that is because the presence of in a fast transistor, when the transistor bit turns on, the channel behaves like a resistor. Okay, so therefore, that we are having some on resistance of the transistor. So therefore, there is a resistor will be there, and also every transistor is having some gate capacitance. Okay, this is the gate capacitance. So that gate capacitance will be represented by a RC capacitor be connected between this point and here. Let us consider this is the on resistance of the transistor, and the gate capacitance can be considered as the one RC section. Okay, so like this, how many sections now? We are having 4 sections in this case. That means one R and capacitor for one transistor, R and another capacitor, another transistor. This is for another transistor, this is the another transistor. That means we are having 4 sections which are connected like this. Okay, so now in this case, what happened when the signal is start from here and reaches the output at this point? So what happened? The signal will be because of the resistance time constant. There is a R and C time constants of the network. So what happened? There is some suddenly that means the will get a signal be exponentially rises. The voltage across the capacitor will be rises exponentially. So therefore, we are having number of sections should be there. So we are having the signal be like this. That means you are having some delay in this case. Okay, exponentially rises like this. Okay, and the maximum voltage is nothing but because of we are using a pass transistors, it's equals to always VDD minus VDP. Okay. Now let us consider the section like this in this case. So assume that this is the one section of the RC network. The transistor can be replaced by one RC network like this. You have the sections like this. So this is the input signal here, and this is the R. That means we are in the same transistors. So equal resistance we can consider, and same capacitance we consider here. And assuming that these are the nodes of the corresponding section. Okay, let us consider the voltage at this node is V1. And let us consider the voltage at this node is V2 and the V3 like this. Okay, and this is the amount of current flow in this resistor. Let us consider I1. In this case is I2, and this is I3 like this. Okay, so now assume that what is the value of I1 now in this case? So now we are going to write the equation of voltage. Any equation can write here. Better to go for V2. Because it's exactly the center point we can consider. The same voltage levels you can see here. So now assume that I mean approximately same. That means we are having this is the voltage V1, this V2 and V3 different voltages. So let us consider the writing the equation of V2. Okay. Let us consider the voltage V2 here. So what happened now in this case? We can write the equation of we are going to write the voltage at this node. Okay. That means we are going to write the voltage at this node. So how to write the equation now in this case? Now just observe here. Okay, let us consider what is the voltage V2 at that means the response of node voltage node V2 with respect to the time is given by. What is the voltage now? C dV by dt. Let us consider the response of the node V2 with respect to the time. Okay, it is given by, let us consider, we know that the current, equation of the current is nothing but the voltage current through the resistor, current through the capacitor is equal to C dV by dt. Okay, C dV by dt. Let us consider now the current through this node is given by C dV by dt. Okay, let us consider the voltage at this node. The current through this capacitor is equal to C dV by dt. Right. So this is the current C dV by dt that is equals to. What is the current now? Just remember, this is the incoming current, this is the outgoing current. So that whatever the concept of the voltage at this node is nothing but I1 minus I2 is equals to this equation, this current. Okay, I1 minus, that means we are writing the equation that is KCL at this point. Okay, so therefore I1 minus I2 is equal to the current flowing in the capacitor. Okay, that is C dV by dt is equal to I1 minus I2. Right? Can write the equation now. I1 minus I2. I1 minus I2, C dV by dt is equal to I1 minus I2. And what is I1? What is I1 here? The current through this resistor. So how to find the value of current I1? Because we are having the two voltages. Okay, across this, the voltages are connected to the terminals of this resistor. There is V1 is one resistor, one voltage, V2 is another voltage, and the current is given by V1 because the direction of current like this. So V1 minus V2 divided by R is the value of the current I1. Okay, I1 is equals to, you can write the equation V1 minus V2 divided by R. Similarly, I2 is equals to V2 minus V3 divided by R, depending upon the direction of current. Okay, so this is the current like this to this resistor. Okay, there is a drop depending upon the one. You can consider the drop of this resistor. So now in this case, I1 is equals to V1 minus V2 by I1 minus V2 minus V3 by R. Okay, V1 minus V2 by R minus V2 minus V3 by R. That is the voltage current through this capacitor. Okay, C dV2 by dt is equals to V1 minus V2 by R, V2 minus V3 by R. This is the equation we get now here. Okay, now this is the equation of the node response of the at node 2. Okay, with respect to the time is gone by like this equation. Okay, now in the, for example, with the number of sections will be large. Okay, the number of sections will be large. Assume that the number of sections will be very high, very large. Then within the limit, as the number of sections the network becomes large, and this expression can be replaced by, so this is R into C, there is cross multiply here, R into C, because the number of sections becomes so large here within the limit. So therefore, we can represent RC into dV by dt. Okay, sections would be very, very large. Now in this case, distance is large now in this case. So RC into dV by dt is equals to, we are having the equation, there is d square V by dx square. Okay, so d square V by ds square, where R is nothing but the resistance per unit length, where R is known as resistance per unit length, and C is equals to capacitance per unit length. Okay, and the X, it is the distance along the network from the input side. Okay, distance along the network from the input side. Okay, how much distance? So therefore, we are having some propagation delay. Okay, so there is some propagation of the signal, and this propagation time that is proportional to the square of the distance between them. Okay, the square of the distance between them, basically. Okay, so therefore we can consider that there is some signal to be propagated, and we are having some propagation time TP for the signal to propagate from the to a distance x, and this is given by, as we know that a propagation time is proportional to the square of the distance between them. Okay, so therefore we can represent tau p is proportional to the value of distance is x here, so square of the distance is x square. Okay, tau p is proportional to x square. So this is the propagation time. Okay, the signal will be propagated from this point to here in time tp, whose value is proportional to the square of the distance between. Okay, so therefore we can consider here this analysis can be considered as can be simplified if you consider all RS and CS are lumped together. Okay, if you consider all RS and CS are lumped together, then we can consider that RS, that is the R total resistance value is equals to how many number of sections we are having, that number n, and small r, where small r is called relative value of relative resistance of the particular section. Okay, so there is like this to get R total is equal to n into small r, and the unit of this R total is we are going to represent in terms of RS. Okay, we are going to represent in terms of RS, right? Similarly, to total capacitance, the total capacitance in this case is equal to number of sections, that is n, into small c, where small c, again we can consider the small c gives the relative capacitance per section. Okay, and the unit of this relative capacitance is in terms of square cc. Okay, remember, in terms of relative values we are going to represent, because we are going to represent the values R and C in terms of relative values. So the unit is for resistance is RS in terms of RS, and the capacitance value in terms of square cc. Okay, so therefore this then the overall time delay of the network is given by of the network is equals to, so what is the time total overall network now? There is a delay, there is nothing but delay that depends upon the R and C. Okay, that is R and C multiplication of the product of R and C is called time constant here. So delay is nothing but time constant, you can say. So tau d is equals to R total into C total. That in case NR into NC, it becomes N square into RC Okay, n square into RC you will get. Okay, just remember. So we're having n square into RC n square into R into C. Okay, n square into small r into small c. Okay, n square into small r into RC. Again RS into square CZ. Square CZ. Okay. This is nothing but we can consider as tau p. Okay, time delay. That is propagation delay, we can say. Okay. So that means this is equals to, we can represent n square into RC, small c, and this one can be considered as tau. Okay, this can be considered as this is the unit. Now let us take unit equals tau. Okay, this is the unit of the cycle. That means the total delay tau d is equals to n square into RC. So the overall delay now in this case increases depending upon the number of stages. Okay, as the number of stages are increases, this delay also increases. So therefore, particularly in case of VLSI integrated circuits, maximum number of pass transistors we can incorporate in order to propagate the signal is 4. Okay, you can only 4 transistors can be incorporated. You can use normally connected in series. So if for example, whenever we require more delay, okay, whenever we require delay is not important, you can use the number of stages, more than 4 stages you can use. But the delay is very, very important in that particular cases. So we are going to use the buffers between the 4 stages. Okay, buffers between the 4 stages. We are going to insert the buffers between the group of 4 pass transistors to reduce the delays in this case. Okay, that is about the propagation delays by using cascaded pass transistors. Okay, so now let's go for the next one. Is called design of long polysilicon wires. You can say. Okay, now just observe. So let's go for the long propagation delay. Let us consider what happened in this case. So sometimes which are this polysilicon? The polysilicon can be used at the input side of the inverter circuits. Okay, sometimes you can use the polysilicon to transfer the signal from one point to another. Okay, because we are connecting the polysilicon layers to transfer the signal from one point to another. So if you consider the distance is very long, very large. So in that case, if you use the long polysilicon wires, what happens? So similar to that of the pass transistors, the polysilicon also contributes some distributed series resistance and series R and C capacitors. Okay, that means the polysilicon is also depending upon the condition. It's also having some capacitance, and also the resistance also present in the polysilicon wires. So therefore, what happened now in this case? Again, there is the chance of a delay. Okay, there is again delay will be exist, so that will be slow down the speed of the signal. The signal propagation will become slow down. Okay, so the compared to there is another case, and sometimes you can use the diffusion layers also. But compared to the diffusion layer, if you use the diffusion layers, what happens? The polysilicon is having less resistance compared to the diffusion layers. Okay, so therefore, whenever you can use the diffusion layers to transmit the signal from one point to another, so because the diffusion layers having the resistance is very high, resistance is very large. Okay, very high resistance. So what happens? The delays will be very, very large. Okay, delays will be quite high in that case. So therefore, whenever delays distance is very short, you can use the diffusion bias to propagate the signal. But whenever the distance is large, in that case, we are not going to use the diffusion layers as a propagate the signal. So therefore, because of high resistance values, so any one value, either resistance or capacitance will be increased. So what happens? The delay will increase. That's why we cannot use the diffusion compared to the polysilicon. Okay, we can use the polysilicon compared to the diffusion layer. Okay, so we can use the diffusion layers to propagate the signal for short distances. But whenever you can use polysilicon, we can transfer the signal for long distance also. But what happens? There is also some considerable amount of resistance will exist, and the capacitance also will exist between the 2 points. Again, you get the same type of delays. Okay, for example, let us consider here. Okay, so in that case also. So assume that this is the long polysilicon wire. So in this case also, we are existing capacitance and resistance for each and every sections here. Okay, so there is a chance of existence of RC delays. Okay, assume that at this point. So what happened in this case? Because of this delay, long silicon wire, there is a chance of delay at this point. Okay, this is the output of the long polysilicon wire. So when the output of this long silicon wire drives the inverter, so what happened? Directly we can connect the signal to the inverter. So what happened? Because of the noise present in the output, okay, with the signal suddenly rises like this, but the capacity output is not suddenly rises here. You will get some time t. Okay, you have exponential rises like this, and because of that, what happened? The output of the inverter cannot be suddenly rise to 0. Okay, cannot be goes to 0 level. But what happened? There is a output will be changing from 0 to 1 and 1 to 0 because of the noise signal. Okay, that is the drawback that exists in the long polysilicon wires. So to eliminate this type of delay, this type of toggling, you can consider as, okay, can be eliminated by placing a buffer stages between the polysilicon wires. Okay, that is the propagation of signal from one point to another. A suitable buffers you can use between the polysilicon wires. Okay, like this you can speed up the, in order to speed up the rise time of the propagated signal. Okay, edges will be rises. So that is about the propagation of the signal from one point to another in case of VLSI circuit. That is in case of integrated circuit. Okay, there are two types of, one is cascaded pass transistors. Okay, and by using a long polysilicon wires. Okay, in both the cases, we are having some drawbacks that can be overcome by placing buffer stages between the stages. When the distance is very short, you can use no problem. Okay, but when the distance is long, then the signal must propagate to long distances. Depending upon the delay, we are going to use the buffer stages. Okay, so whenever we require long delays, long delays are not problem in the circuit, then we can use that directly. The polysilicon wires, delay is not important, then we can use the long polysilicon wires. But whenever the delay is very important, then for example, the delay will affect the output stages. So that then we can use the buffer stages between the stages here. Okay, that is about today's class, right? So in the next class, we can go for the wiring capacitance and then fanning and then choice of layers. So, right? So once again, just remember, these are the important topics, but you have to consider these two are very, very important. Just remember. Okay, no problem. From the examination point of view, these are the you have to remember. Okay, these are the problem that exists to propagate the signal from one point to another. Okay, so in the next class, we go for the wiring capacitances, and then we go for the fan in and fan out, and then the choice of layers. Okay, maybe take some time. After that, we can solve some problems in this chapter. Okay, the problems are also very, very important. Okay. So I'm going to start the screen now. So go back.